Okay, so we're going to go into some details, the definitions and meanings of the math operators del dot and del cross, and kind of like explain a little bit about the meaning of things like divergence and curls and so on. Okay, and then kind of like maybe relate to what they actually showed up in the Maxwell equations. Simply speaking, the del operator is a differentiator vector, and it can be applied to a scalar to become a vector. In that case, it's a gradient, so that result is a vector. But in the context of the Maxwell equations specifically, we don't show any of the delta V, so to speak, so we're not going to talk about that in details here. The other two operations that you can apply the differentiator operator on is a dot multiplication, which now becomes a divergence. And simply speaking, this dot, this del, has three x, y, z component in a coordinate system, the arcs. X is this angle, y is direction, y is this direction on this wall here, and z is the one that goes straight out from the wall right to you. And keep in mind that order x, y, z, x, y, z, because pretty much everything we talk about will be using the so-called three fingers of the right hand rule, the corkscrew rule, and they follow that rule, x, y, z, and so on. So when you multiply the differentiator operator del and apply that to a vector, by definition of vector dot multiplication, which is this first line in here, when you multiply vector A and B, you got a scalar result, which means it's not a vector, it has no direction, and simply it's a quantity that's equal to the strength of A times the strength of B and times the cosine of alpha. It is not unlike you project vector A onto vector B, and that's all there is to it. So when you multiply the differentiator operator del to a vector, let's say D, because the sine of any cosine of any 90 degrees or pi over 2 is exactly equal to 0. So any cross multiplication between, let's say, x and y and x and z becomes 0. So the only thing that you have left would be the like direction products. That means the end result you have is the d over dx times dx. And likewise, d over dy times dy. And that means this is the derivative versus x of the component dx. Because the other cross-axis multiplications becomes all null, right? Now the curl of the del cross is a little bit complicated. The result is a vector, and it follows the rule of vector multiplication, meaning cross multiplication. The end result has a strength of A times B times the sine of the angle that is formed between the two vectors. And by the way, these two vectors don't have to be touching at one point, right? They can be anywhere, but you can just imagine that you have them touching at one point. And it is in the direction that is perpendicular to the plane that is defined by the two vectors A and B, but with the direction that follows this rule of the three fingers, right hand three fingers rule, which is if you multiply x to y, you got a z, meaning x is here, y is here, then z will go out like this, right? And so x times y equals z, but y times x will be minus z, which is the other direction. So that's the definition of the vector cross or vector multiplication. So it becomes a little bit complicated, but when you write it down maybe a few times, it will become pretty obvious that there's a order for you to write that. For the x component, you will take differential with respect to y of z component minus differential of z with respect to y. So for the z direction, you're going to take differential with respect to x of the y minus the differential of the with respect to y of the z, the x. I think, trust me, it would become very natural after you write it and then you think about the right hand three finger rules of x times y is z, and then that order. So what does it mean? What does it mean by divergence, and what does it mean by curl? Divergence simply here is a scalar quantity, meaning it's just an indicator of how much change that you accumulated between at that particular point in space. And that means you have a vector d of a certain thing, could be electric displacement density, that you say, I wonder how much change it would happen at that point to d. Then the del dot d will be simply become the sum of the differences, not differences, sum of the differentials or delta microscopic changes with respect to each direction. So if in the direction x it changes by so much with unit length, then you add that to the change on the y direction or y-axis, and then so on for the z-axis. Curl means like this. There's a visualization that textbooks often mentions, which is, think about a surface like the surface of water in a stream or a lake, and then you have a leaf that's floating on that surface. Now you'd be interested in the degree of rotation of that leaf on that surface, and that surface is defined by the two axes, x and y. So at one point here, you have the leaf is moving at a speed of ex in the x direction and ey at the other direction. And by the way, E here is because when we go back and we talk about electric and the Faraday's law, it means pretty much the same thing. So at this point, which is different from the original point by a distance of dx in the x-axis direction and dy in the y-axis direction, the velocity of that at that point now is differ from that in the sense that it is now, because it is separated by the distance dy, so the change will be equal to the original ex plus the delta of ex with respect to the y direction, the change in the y direction, times dy. So I think if you think about all the differential meanings and so on, this makes a lot of sense. And by the way, I put these in parentheses to denote that they will show up as a minus when we talk about the rotation, or when we talk about the closed loop sum of all these segments later. So this is minus, and this is going to be minus in those calculations. So when you talk about how this leaf is affected, and you're interested in the the z axis, which is perpendicular to the surface of the lake. On one end of the leaf, it is pushed by a velocity called ex. One other end, it is pushed by a velocity of ex plus the change in ex with respect to y. Okay. There actually is another component of changing in ex with respect to x2, but it just getting into the second order of importance, so we leave it out at this point, right? So the delta, let's say if the rotation is clockwise in this surface, then ex adds to the rotation, and the delta here, which is in the parentheses, meaning negative, is actually working against the rotation. Clearly, if the rotation is like this, then this adds to the rotation, and this one works against the rotation. That's why we put it in as minus, right? Likewise, you have at this, you have a new ey component, which is the original, plus whatever the change of ey when you move it from the original to a location which is offset by dx, and that is a plus, right? And now so for the y direction, you got this change, which is a plus here, and then you subtract this part. Okay, so all said and done, some of these cancel out, and what you end up having is this part, which is what we have written here. So that's the meaning of curl. So visualize that as a rotation of a leaf in the xy direction, and how the speed of the water affects the rotation. Now, if you have a leaf falling through the air and it's rotated whichever way, not just in the, we're not interested just in the z-axis direction, but also in the x and the y, then basically you do the same calculation for the other two rotation axes, x, y, and then you have a composite x, y, z, and whatever that is, right? So that's the general case. Now, let's stick with this and then look at something as simple as the Faraday's law, which says that anything, the path of all the electrical vectors around a loop is equal to the change of the flux. That means, again, dot meaning derivative with respect to time. So the Faraday law say that the sum of the integration around a closed loop will be equal to minus, just because the way things are defined. So the change of the flux, meaning the B, the magnetic flux, that is going through that whole area that is defined by that closed loop. Now, what it means here is, if you think about taking E around this minuscule ds, which is dx times dy, you end up having exactly the same calculation. You come out to be about exactly the same. And that's say that at that minuscule or microscopic level, this b here, the derivative of b with respect to time, is equal exactly to the z component of the curl of E. And this eventually we're going to bring it back to the Maxwell equations and see. So that essentially is the meaning of the two math operators that show up in the Maxwell equation. One is measuring the amount of changes of something like the electric displacement density. If there's a charge, it may go up. If the charge is negative, it may go down, and so on. And then the other one is used to describe the change of something like an electric field because of the presence of some form of a time varying magnetic flux. Okay, so let's stop at this point. And the next one I'm going to go is I'm going to show you the visualization of the two integral theorems, the divergence theorem and the Stokes theorem. Thank you.